Oh, I should put in my
Right.
tooth.
So let's see. Hold on. Okay, yeah, we're live.
Okay. You see the three screens? I just can't check.
Yep,
All
we're
right.
good.
Okay, good. Hello, welcome to Corecast. I'm your host Tim.
I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. I know we've been gone for a few weeks, but we're back, and I know this is also a strange time, but due to logistical challenges, this was a time that we could do it at. And so a few other things. If you haven't already, do join our Discord channel, and if you're watching on YouTube, where we try to do this every Tuesday, except we're doing it Wednesday. We do typically 5 p.m. Pacific, 8 p.m. Eastern. So without further ado, let's get to it, Tim. So and Tim and Mikey. So I guess Mikey, I'm just gonna start off asking you this. What is the next breakthrough in physics going to be? Go.
Wait, physics or particle physics?
It can physics or particle physics. Go for it.
Well, yeah, I guess so. I guess we're going to say fundamental physics, right?
Yeah.
It's unclear what the next big breakthrough is going to be, but one thing that's for sure is that it will involve the discovery of new particles.
Hmm.
Yeah.
What I guess what makes you say that? Because there have been all these like advances in like computing and whatnot. Why couldn't the next biggest breakthrough in particle physics be like some type of like quantum computing type of thing instead?
It could be. I guess I wouldn't call that like necessarily like particle physics. So in particle physics, when we say like a new discovery, what we're really talking about
Hmm.
is discovering some new phenomenon of nature, like something that nature does that we've never seen before. And for reasons that I guess we'll get into in the rest of this episode, whenever you discover a new phenomenon, like some action that nature makes, there's always some particle associated with that phenomenon.
Yeah.
Does that
Gotcha,
sound weird?
gotcha.
I think it does sound a
I-
little weird from people who are not in particle physics. You can ask the question, well,
Yeah.
why the heck is that true even? Why would we suspect
Uh-huh.
that to be true? But first of all, there's a historical precedent. Let's add that. Like the recent big discovery was the Higgs boson. It confirmed it was the last piece of the Standard Model. And then before then, I think it was the top quark. It confirmed that there are three family of quarks. And then there was the W and Z bosons. A lot of people may not know that, but that's the confirmation of the unification of the electromagnetism and the weak forces. And then you might kind of scratch your head and wonder, why these breakthroughs always involve new particles. I think there's a very good theoretical basis for that. But of course, I mean, you could argue that there's a little bit of selection biases, right? Like the detection of gravitational wave is not a new particle. The detection of black hole mergers.
No, but there is a particle associated with it.
Yeah, exactly. So I think it's fair to say that there's always some level of particle association with a discovery. And there's a very good theoretical reason, which I guess we'll dive into a little bit.
I guess can we take a step back and maybe tell the audience like what is a particle? Because back when when I was learning physics, let's say in undergrad or even high school, learn a particle was like this point-like object, or in the case of quantum mechanics, is a wave. But is it like deeper than that? Like when can you say you have like discovered a particle, historically speaking?
Yeah, I think like so typically when we learn about, particles, we're in high school or college or whatever, like it's very ingrained in us that a particle is like a constituent of matter. It's like what makes up
Mhm.
like a desk and a chair. It's all made of particles. And so we're used to thinking of particles as like sort of like building blocks of stuff. But it's actually much deeper than that, because particles are not only the constituents from which stuff is made, but it's also the constituents from which phenomenons are made. The simplest example people learn about is like the electromagnetic force, right? Like two magnets attract. Turns out there's a particle responsible for that. Like when two magnets attract, they're actually exchanging a particle of light, which we call a photon, which basically communicates this force. So particles are not only the constituents of all stuff in the universe, it's also the constituents of all phenomenon. So if you discover a new phenomenon, there's going to be some particle responsible for that.
I think we can be a little more specific though. I think the reason particle is so fundamental is because particles is a very universal thing, and in most cases there are particles associated with a phenomenon, like what Michael was saying. For example, if I hit the table, there's some sound waves, propagating the table. You hear a loud thud, right? And those sound waves you can think of as some sort of jiggling of the material, and you can also thought of them as some type of particles. And in condensed matter physics, we call these phonons, right? These are particles of sound. And in a very similar vein, all the stuff around us, we know that in fundamental physics, are built from what we call fields in an abstract way, just some kind of a substance that's permeating all of universe. And the jiggling of that, the individual jiggling, if you are able to separate them, are the particles. So even though conventionally in high school you learn that, hey, particle is like a point-like thing, that's not exactly the truth. Particle is just some very generic consistent jiggling of things. And that's why it's so ubiquitous.
So then I guess, Tim, one question regarding the example you gave. In that case, like you have in condensed matter physics, in particular materials, or even, even in air, you have like the propagation of sound, and that produces these particles that they call, or I don't know if you want to call it particles or quasi-particles, called phonons. But we don't, when we look at like the standard model, we don't see like phonons as like a particle listed in there. What gives?
Yeah, and indeed you don't. Like what we really care about are the fields themselves. So the standard model tells you that there are these substances that permeates the universe that stuff is made of, and they interact with each other. And you can argue that the standard model isn't just about particles, it's about these fields, right? But then experimentally, you can ask, well, how do we definitively make sure that these fields exist? Like we can't touch them. We can't, I don't know, like we can't just grab a field and feel as influencers, right? So the most direct way to do it is really to just, I guess to use a good analogy, just get a hammer and just whack the field hard enough so something comes out of it, then it's a definitive confirmation. So that's why I think, and that's why, and that's why particle physics is called particle physics, right? It's the idea that, to confirm that something exists, you have to whack it so hard that it produces enough disturbances for you to measure it. So to really, really confirm it.
Can we, I guess, like give an example of like what it means to like whack something with a hammer, like in this analogy that you gave, and like you also gave the explanation that like basically we look at these fields, and if there's enough of a disturbance in the field, then we say it's a particle. But like how do you know like how much disturbance is enough? Like at what point do you say, oh, this is a particle, versus like, oh, this is like some background stuff, I really can't make it out? And like what is it that you can't make out per se? Like if it's a field and it exists everywhere, couldn't you say the particles everywhere? What does it mean? Another example is like, if I look at like a proton and like I say there's a proton there, what does that mean? There's probably a field that describes, proton in general permeates the entire universe according to this model, but yet I can say locally there's a proton like right there, like in, hydrogen gas or whatever. How do
Yeah,
I say that? That's my question.
yeah. I think we should break this question down into two parts. First to explain this, how particles lead to discovery. I think it's good to use an historical example. Mikey, let me know if you agree with me. I think the weak forces that's responsible to radioactive decay was a good example, right? Back in the days, we see that nuclei can decay, like a neutron. If you take a neutron and you just let it sit around for 15 minutes or so, it will spontaneously decay into a proton. plus an electron and a neutrino, right? And you can argue that, if you didn't know the weak force, this is a new phenomenon. And how exactly do we confirm that? So of course you can directly measure the decay of neutrons, and you can argue that, hey, neutrons decay, that's a new phenomenon. But that's kind of not enough. You haven't really explained the decay phenomenon yet, right? I think back in the days, you're like, hey, we can build some models, how neutrons can decay, but that's not like a fully consistent model yet. To really have a fully consistent model, you have to say, like, hey, there's some new forces that generate that kind of decay, and if there exist new forces, that means there's a new force field associated with that, and this means that you could jiggle this force field hard enough to produce some new particles. And I think many years later, I don't know the historical context. I think at CERN, I think it was at LEPT, when they collide electrons and positrons together, they were able to produce those really heavy force carrier, W and the Z boson, and their properties matches the ones that come from the neutron decay. And it is only then they're able to claim that they've really understood radioactive decay, really understood that phenomenon theoretically, so they can really claim the discovery of the electroweak force. And I think the Nobel Prize was awarded afterward. Yeah, I think that's a good example. I think, Mikey, do you know some other historical context for that?
Wait, sorry. What was the question again? I mean, you said there was two parts to this.
Well, the part was that it's like generally we don't see particles floating around. Like, why is particles required to make these discoveries? How are they relevant? But historically, just observing a phenomenon isn't enough yet for theoretical understanding. And in the electroweak case, we have to whack the field hard enough to produce W and Z boson to confirm it.
Oh. I thought Sahil was asking, what does it mean to say that there's like a proton sitting there?
That's the second question.
That's
I
the
guess
second.
like my question is, how much of a disturbance is needed with your figurative hammer that you're whacking, or literal, whatever you want to say, for me to actually call something a particle? Like if I like smash this desk, like how much disturbance do I require to actually say like, oh, there are like these particles there?
I don't know. I think that's people might disagree about that. I would say any amount of smashing.
No,
Right, because like, huh?
I think there's a level of threshold, right? If you look at the neutron decay example, if you don't hit the neutron hard enough, the neutron just very happy to decay, and the WZ bosons are involved, but they don't really, they kind of really don't make an appearance for you to discover it. They kind of, you only experience the force, the residue, the residual of the force. So you can't really examine it in greater details. So I think in this case, there's a level of, to really see the electroweak effect, you have to inject enough energy to kind of excite the field in some ways, because the field could be pretty rigid, right? I don't know, does it answer the question?
Yeah, I feel like well, I don't know. The way I would think about it is like in terms of smashing a field with a hammer, right? It depends on what kind of particle you're talking about. And I guess the subtlety here is like if we're talking about, some particles have some amount of intrinsic energy, which we call mass, and some particles don't. So if you wanted to create photons, then you wouldn't need to smash the field very hard at all. Any kind of disturbance would produce a wave, and any kind of a wave, you can always imagine a wave being made up of a collection of particles. But if you're trying to produce a particle that has mass, that means it's still a wave, but it's like a wave that's sort of stable. It's sort of like a standing wave. And in that case, you need to smash it with enough energy that's equal to the mass of that particle, according to E equals mc squared. So yeah, I guess in terms of your question, it's like it's kind of tricky because if we think about like wave particle duality, there's literally an equivalence between waves and particles. But if you're talking about a particle with mass, that's a little bit trickier because there's something called a mass gap where you need like it's sort of like a hill you have to get over in order to create this particle. And
Mm.
that the steepness of that hill is proportionate to the mass of the particle you're trying to create.
Yeah,
Huh.
I wonder if it's a good idea to bring in the Higgs boson analogy, right? Um, you can ask the question like, why is the Higgs boson needed? Why do we have to had to discover the Higgs boson? The reason is that if you look at interaction between some of the W boson, I mean it's a little technical. These are particular fields that exist for that's responsible for radioactive decay, right? We observe some level of anomalous behavior, right? Basically, there are two types of discovery in particle physics. First, you can just say, hey, there's some new particles. Sure, then there are new particles. Or you can say, well, there might be some new interactions between fields that we already know, right? And then the question why we haven't seen those interactions is because these interactions are very complicated. And usually what that means is that uh, these are very subtle shifts in some of the numbers that we observe, very subtle differences in interactions. But then the more energy you put into the system, like for instance, you can say, what if four W 4 electroweak field come in and they have this new interaction? You can say that. What if that exists? It usually means that the more energy I put in, the more pronounced that subtle effect becomes. And at some point, when I put in so much energy, my mathematics become a little out of whack now. This effect can become really, really large, right? And in order to resolve the issue, to resolve this number from blowing up to getting very large, usually it requires the existence of a new particles. Basically, you whack enough energy, and instead of having this interaction blow up, it just creates a new particle. And in this case, for in the electroweak case, we create the Higgs boson. And indeed, that's one of the ways we discover the Higgs boson is we whack these fields with such high enough energy at the Large Hadron Collider, a Higgs boson come out, and we really confirm our theoretical understanding. So I would say the energy required to create this new particle is kind of, I guess, depends on how subtle these new interactions are.
Mhm. I see. I see. So would you say that like so you're talking about WZ bosons? I assume they're quite heavy, and so in order to actually observe them, you need to smash a hammer with such an amount of I guess like energy such that it's on the same scale as their mass. Is that a fair thing to say in order to actually observe them?
Yeah, exactly,
Yeah.
exactly.
Mhm.
Okay, okay. I guess then, so okay, so I want to come to a little bit more concrete example of things involving like particles that already are there, like say like a hydrogen ion, which is simply a proton. Let's say I have a proton by itself, and you've talked about this field description of like there's this field permeating the entire universe. Let's say the or it can even be an electron by itself. Let's say there's just a single electron by itself. There's a field associated with this electron. Yet I like, if I throw light at it, at this electron, I can observe that it's like, localized to some region in particular. I was like, so I'm wondering, like, from a field perspective, what am I exactly like looking at per se? Like, how can I say that this thing is here? Like, does it have enough of a disturbance here? If I throw enough energy at that one spot, I'll get a whole bunch of other, a whole bunch of other stuff appearing. Like, I'll get WZ bosons appearing. I'll get, other particles appearing. And so, like, what is that kind of balance between like throwing a lot of energy at it versus like a minute amount of energy? Or like, how do you think about that?
Yeah, I would say that the kind of experiment that we're talking about in particle physics, it's a little bit
Mm-hmm.
different from the everyday experience. Like when we see that we observe a proton or electron, yeah, even though these are particles, they are
Mm-hmm.
they are not they 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 are not just the excitation that we're talking about, like whacking a field, right? Like for example, the proton is actually made up of many different particles. It's a very complex collective phenomenon of many fields coming together. There are gluon fields coming together, there are quark fields coming together. They're all interacting and causing this very complex bound state of what we call a proton.
Mm-hmm.
And similarly, the electron isn't all that simple either, right? Because there's the electron and there's the cloud around the electrons. There's a lot of electromagnetic field interacting. And in a similar vein, if you get really close to the electron, you can see a lot of these very complex interactions. So these, even though to us they seem like simple particles, they're not just simple particles, right? But in particle physics, when we smash them together at very high energy, we're talking about very complex collections of fields interacting, and also many
Mm-hmm.
collection of fields coming out. And the result experimentally is not easy to interpret, right? There's all these multiple. In fact, most collisions, you see multiple particles coming out, but the analysis is done such that we isolate each, if you like each pixel of the outcome to a simple interaction between fields. So I would say the language that we use, like, oh, let's say the electron interacts with the photon field. Right? It's a very simple interaction. Electron sees a photon, it gets a kick. Right? That's a simple interaction. That picture, when you sum it up many times, infinitely many times, will manifest in the behavior of an electron sitting in our hands. Right? So it's not a direct one. It's not a direct simple comparison, I think, and that's maybe making it a little harder to relate from the theory to the everyday world.
Wait, you said an infinite. Where did infinite come from?
Right, because an electron has electric charge, so every
Yep.
second or every nanosecond is interacting with itself electromagnetically, right? It never stops. Even though when we collide particles, we talk about, hey, one collision, one thing comes out.
Mm-hmm.
But in reality, there's infinitely many things. But
Wait, how? Mhm. I was curious. How is an electron interacting with itself? What does that mean?
yeah, I mean, it gets very complicated because the electron has charge, and
Yeah.
charge can produce it can produce photons, right? And
Yep.
the photons also interact with charges. So
Yeah.
in quantum physics, the outcome is the sum of all the possibilities. So
Yeah.
you kind of have to sum all that up in order to get the
Mm-hmm.
behavior of an electron even just at rest, right? The electron can, because it has charges, it can emit a photon. The photon can
Mm-hmm.
interact with itself back, and so on and so forth. So you have to sum that up.
Mm-hmm.
In fact, you can have more complicated. You can have chains and chains of more complicated stuff. You can have electron emitting a photon. The photon could split into electron and positron, and those can emit
Mm-hmm.
another photon, and then those photons can
Mm-hmm.
interact back with the original electron. So all these have to add up together. It's kind of crazy, but somehow we can approximately sum them all up and get something sensible. Um,
Huh. Mikey, what are your thoughts on this matter?
Um, I forgot what we were talking about. It got too complicated.
I guess the original question is that, like, if I see an electron by itself, and with this like field description that Tim had given, that like there's this field permeating universe for each like particle, and let's say I see an electron, and I use "see" in quotes because I'm literally throwing photons at it to measure where it is. If you throw enough photons or a high enough energy photon at it, then anything can happen. Like you could get protons and antiprotons that
mm,
appear. you get all these other things. So my question to Tim was like what is the kind of the balance between that of like, if I what does it mean for like an electron to be by itself? Because this whole notion about I don't require to smash it. It's like it's there. Like what?
Ah,
Yeah.
okay. Okay, I see. So I think what Tim was referring to is kind of the idea that, like, technically speaking, an electron is never just there by itself.
Mm,
But I think, to like, the way I would like address your question is like, and actually I would disagree. It's not like when you shoot photons in, anything can happen. If there's an electron there, there's a very specific set of things that can happen. If there's a proton there, there's a very other specific set of things that can happen. And this, I think, whenever we observe anything,
mm,
right, we're never observing it directly, right? Like, you shoot something at the object and
yeah.
stuff comes out, and the stuff
Yeah.
that comes out goes into your eyes. And
Yeah.
that very unique pattern that your eyes perceive allows you to perceive that, that was an electron there. If there's a proton there, you shoot things and then some other pattern comes out.
Uh-huh.
And then, your detector might recognize that as a proton instead of an electron. Um, yeah, it's very, each particle will cause a very different kind of signature, I guess you could call it,
Mm,
stuff that goes out for whatever you throw into it. And I think that's really what it means to say that there was an electron there versus a proton there. It's, you shoot stuff at it. Yeah, it's true, if you shoot it up with high enough energy, all kinds of crazy stuff can come out. Um,
yeah.
but it's very different. The kind of stuff that would come out is very different for an electron than it would be for a proton. For example, conservation of charge would demand that if you shoot a bunch of photons at an electron, a bunch of stuff comes out. When you add up the charge, it has to be -1. If it's a
Yeah.
proton, you add up all the stuff, it has to be +1. So that would
Mm,
allow you to distinguish an electron from a proton, for example.
mm. That makes sense.
Yeah,
That makes sense.
yeah, and I guess to add a little bit of realism to this discussion, like how do particle physicists discover new particles? The way we do it is to analyze these intricate patterns to see new rules. Like what Mikey was saying, oh, if you have a proton, you can measure all the things that come out, and you realize that when you add them all up, you might get like a positive charge. That's not obvious. This will be different if you started with one electron, that would be a -1. So there are these overarching rules that no matter how complex the pattern is, it has to obey something, right? So a new particle usually
Hmm.
manifests itself by what we call like a resonance, like a mass peak, right? You might take some of the pixels that come out, analyze it, you can compute a mass, you might see a very
Hmm.
sharp spike, and this will tell you that hey, there's kind of a new pattern in these interactions, and you can make an inference. You can infer that hey, look, this means that there could be new fields, new interactions, and that's really what we're looking for. I mean, even though particles it sounds so tangible, it's like hey, something I can grab a hold of. But in reality, it's not really that.
Hmm.
It's just like hey, there's some new patterns in the interactions that exist, some rules, some specific thing we can examine. So
Yeah, I would agree with that. Yeah, and if you think about it, that's really what the root is of all observation, right? It's the detection of these patterns. Like, I can identify that there's a table in front of me rather than a chair, because the light that scatters off of it creates the pattern of a table when it hits my eyes. It's very similar to what you'd imagine scattering off particles.
Hmm. That that is interesting. That makes sense. That makes sense. So I realize we're almost at time, and Mikey, I also know you have another commitment to go to. So I wanted to give you guys a chance if you want to leave the audience with any parting words.
Yeah, I mean, I don't know. I guess as a particle physicist, it's kind of like, um, one of the things that irks me is like when you tell people you're a particle physicist, it's always like, okay, so you study particles, and that's like one specific thing. Like, and then someone else studies astrophysics, and that's another kind of thing. I feel like that kind of like undercuts um, how universal, as Tim said, like the idea of a particle is. It's not just limited to the constituents of matter. When we say we're particle physicists, what we really mean is we study everything that could possibly happen. Um, because anything that can possibly happen can be described as particles.
Mm,
yeah, I would like to kind of add to that. a particle really is just a distinguished, isolated pattern that you can extract from, from the fundamental laws of physics. So, and that's why you can argue that many things, they are particles. Like, if there's a new force, there's got to be a particles. If we don't know what dark matter is, you can have different theories of dark matter, but the fact that dark matter moves, it has mass, and it has these properties, it's presumably a field. That means it's made of some type of particles, right? So all these phenomenon, all these, and recently we saw news about, there's a lot of news about there's some subtle properties of the muon that was measured, and a lot of articles says there's a new force, the fifth force. And we also know that, hey, to really confirm it in the future, we probably need to produce a new particle to really claim discovery. And to that end, yeah, the term particle really is just emphasizing the, I don't know, like the what is it, the pinnacles of the scientific discovery, right? It's not enough to see phenomenons that are anomalous. Oh, something doesn't match. We want to grab. We need to have a way to almost like interact with that new phenomenon, and that interaction is the creation of a new particle, and that's why these ideas in particle physics are so powerful.
That makes sense. That makes sense. Well, I think those are fine parting words. And so on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week.
Yeah.
Bye.
Bye.
Bye.